Huh? You're not talking to me?
Oh yeah, I wasn't.
Okay. Oh, that looks better. Okay, so we want the top two surfaces. So what we're going to do is we're just going to start. Now, just to avoid making a super complicated script, we're going to, and I'm just also going to put this back to the way that I like it. Preferences, palette. Okay, that's better. Okay, so what we're going to do is we're only actually going to work on one segment, right? Because your segments repeat, yeah? So you only have to work on one repeatable element to work out how to make every single element that's required, yeah? So we are going to, these are all in lists because did everyone end up using that extrude to point thing that I did in the video? Those of you who follow the video, you know that how I did like an extrude to point at the very end? And that was really like quick and handy way of doing it. Well, I'll talk about how to get that into a system like so. But so for now, we'll just stick to these particular panels. We just want one of these, right? So if we can see that there's 6 of them, so 0 to 5. So there's 6 panels, and if I select it, they're highlighted in green, but we only want one, okay? So if I were to just quickly, if you were to quickly describe that, what would you do? To get one of these out of what would you do? Without using Grasshopper, just thinking like pseudocode, what would... Separate? Like if you wanted me to get one of these out of the list, what do you do? What do you say to me? Delete. Delete what? Delete the surface. No. Okay, so if I've got a list of students, right? And you want me to talk to, so there's 4 students here. You don't know their names, huh? There's 4 students. We don't know their names, so there's 0, 1, 2, 3. And Jamie, you need to tell me, you need to give me instructions on which student I want to talk to. Which student should I say something to? So give me that instruction. Pick a random one. No, you get to decide which one I talk to. Okay, so first one is
0.
Right, so which one do I talk to?
0.
So Andrew, talk to student 0. Right, that's the instruction. That means I'm talking to Curtis, right? So if I were to pick a student, you need to define the index that you want to pick, right? So if we want to pick out, let's say, the first item of this list, we can use list item. And by default, list item is already picking the first item. So we can see that with list item, we're only getting 1. And that is because the index, the I, the element that goes into I, so if I have this go up to 5, we are telling it to pick out element 0, 1, 2, 3, 4, or 5. Yep. So we just want element 0. Yeah? Does that make sense? Yeah. So this is just like me picking Curtis out of the group because he's the first one in the list. Okay? So we need to do that. Oh, no, let me just put bifocals on. Blink. So we need to do that with every list here. So we're going to copy list item and just maintain the elements, the index. So that's now set this so that we can we've now got the, and I'll just hide these points. Now we've got that one segment of the model. Yeah? Does that make sense? I'll just go back. So if I were to put in -1, what do you think I'll get? Do we remember what -1 means with a list?
Yeah, it's the last one.
Right, so we'll get the last one. So it'll go that one. So we'll use the first one. So we use item 0. And so from here, we want to take, we're going to work with these top two elements first, okay? So with these top two, we're going to work out how to do the first triangle, right? So we need to draw an outline of this triangle in plan so the laser cutter can cut it out of plywood, yeah? So in 3D, we now need to work out where this triangle intersects, and where does this triangle, the triangle in green, where does it need to be finger jointed, okay? Where does it need to be finger jointed?
Joining lines of those surfaces. The joining
So,
line overlapping the other.
so it needs to be finger jointed here, yeah?
Yeah.
And also here, right?
Yeah.
But let's just remember it's also attached to another triangle, yeah? To the left and right. So there's actually, like if I quickly do this, so remember it's got a triangle to the right of it as well. So it's going to have a finger joint also on this third one, and we'll deal with that in a step further along in class, okay? So the first step we need to do is work, yeah?
How did you hide the rest of it?
When you select things, you can select things, hit spacebar or middle click, and then click the little guy with the blindfold.
What should I hide the other surfaces?
What I've done is I've just see all these inputs, I've just hidden them so that we're just seeing the ones that we've isolated.
Oh, I see.
Cool, okay. So, first thing we need to do is we're going to create the finger joint intersection between this edge and the one adjacent to it. So if I were to highlight the ones in green, it's the edge that is between them. Now there's actually some really clever ways of doing this, but with really advanced scripting, and we're going to avoid that, okay? So I just want you to know, long term, the process that we're using today is something that I really hope I wouldn't see in maybe like an intermediate scripter's repertoire, and they would avoid some of these things, and I'll point out where they are. But what we're going to do first is we're going to find the intersection between these two surfaces. So do you remember how we had a plane intersecting with a surface or a B-rep? Yeah? So the plane effectively cut through and it created a line. We're going to create a line between this surface and this one where they intersect, and that's going to be the edge. So under intersect, under B-rep intersect, if we then plug these two in, that'll work out that they intersect at that line, and that it's a tentative intersection. So if any of them move away from each other, then it's not going to intersect at all. So you can find that here. So that's going to create this line that it'll help us effectively, then we can use that line to create a finger joint. And I'm just going to I'm really more so going back to this because we've this thing can get rather complicated. Okay, brilliant. So that's what I thought. So what we're going to do is we need to generate a finger joint system on this, and we're going to create patterns to finger joint. And it's probably worth actually talking through a pseudocode of what finger joints are. And then we also have to generate a plane for this finger joint to work on, because we're now working in 3D. So we're not working in 2D, we're working in 3D, and we have to start defining planes. We can't just say the world plane. So, but first, if I were to take a line and I want to generate a finger joint as an outcome, okay? Actually, let's leave that off the end. Let's do, do you remember what we did last week, how we sort of stepped through and we worked out exactly the steps that we wanted to take? Let's do that now, guys. So who wants to take a stab at step one? We've got a line, so we obviously don't need to draw a line. What's step one?
Divide it into sections.
Okay, so divide into sections, and they have to be even?
Yes.
Okay, so we're going to divide it into even sections. So there we go. Then Arlene, that's it. That's you're out. Next step. We've divided into sections. What's another step that we can take?
Maybe use a split list or a list to select every second.
Right. How did we do that last week? Remember how we had a list of points, or a list of numbers? 0, 1, 2, 3, 4. Do you remember how we said, okay, take all the odd ones and all the even ones, and we can create a pattern for them? So we can create a pattern that dispatches them, right? So effectively, we could say true, false, false, true, false, true, false, true, false, true. Yeah? So we're defining these into two separate lists. Then what do I have to do?
Duplicate the line.
We don't need to duplicate them. So let's say you can now tell me, grab everything that's labeled 0 or grab everything that's labeled 1. So what do I do to everything labeled 0?
Write a list for it.
Okay, it's already in a list. So it's in its own list of zeros and ones. Now, yeah? Next step. What do we do to these? Let's say we've got a list of zeros. Now what do we do?
Can you shift them?
Shift them. Okay. So move them.
Yeah, move them.
Okay. So we'll move them up. Right. And then now so these don't exist now. Yeah? And then what? We're almost there.
Connect the ends of the moved line.
Yeah, so we need to connect the end of the first line in this list with the end of the start of the first line, and etc. And basically, we'll talk about how Grasshopper does that very soon. But does that make sense? It's a really simple process, and I just want to be really careful about when we say shift, because if we just think about Grasshopper context and syntax, shifting a list means that if this was index 0, 1, 2, 3, then we've shifted it so that they're wrapping. So what other word would you use? We've used this function last week. What did we do to this curve to put it at that location? We moved it. So that's one way of doing it, right? But I want to be really careful here, and order matters. So if I have a curve whose start is at the top and its end is at the bottom. Can you see? And I have a curve that start is at the bottom and its end is at the top. And we create this finger joint system and we tell it to move, right? So if I were moving this one, which way would it, let's say I want to move left, right? It's going to produce a finger joint like so. And this one would also produce that. But if I then also had a curve that did this, and I told it to move left, then the finger joint would look like this, yeah? Because so we need to be very careful about when we say move, because move requires a direction that it needs to go. So a much better way to deal with that is to say offset, okay? Because what offset does is, in this case, it'll offset in this direction. So offsetting that way. But if I have a curve that goes in the other direction, then the offset will end up going this way. Because if we have a system that's effectively counterclockwise, then offset will mean out, or if you do negative offset, that will mean in, okay? And this is going to be really important. So we'll go back to doing this finger joint. We've got a line. We need to start splitting it up into segments. So last week we used divide to create points on a curve, but we don't want that. We actually want to break our curve up into segments. And the component that's going to do that for us today is shatter. What shatter does is it takes parameters and it'll break your curve up at the parametric locations that you input. So if I were to put a curve in and reparameterize it, just to do a little test from whether or not people were listening last week, and I were to then plug a slider in at 0.25, can Scarlett, could you describe the type of curve? Where would the curve get split? Would it be easier if I were to say, if I were to put in 0.5, now I'm getting two curves as an outcome. Yeah? If I were to say this pen is the curve, and I were to shatter it at 0.5, where on the curve would it be shattered? Can you point? So if this is 0 and this is 1, then 0.5 is going to be in the middle. So we're going to, I'm not going to break the pen, but we're going to have we're going to have half a pen on the left and half a pen on the right, right? So if I'm using 0.5, I'm going to get a split in my curve in the middle. So we can see these two curves, and if I were to highlight one of them just really quickly with this, then we can see, ooh, that's interesting. We can see that it's split at a point, and for some reason the reparameterizer is being a bit funky. Oh no, that's because it's 0.25. If I made that 0.5, then it's going to be in the middle, of course. So you can see there that there's a really faint green line that only goes to the middle. Cool. Okay. So, but we don't. Yeah.
So it takes the parameters and then splits it.
Yeah. So instead of getting points, you get line segments. Yeah. Which is it's exactly what we want, right?
Yeah.
We didn't want the points. We want the line segments. Yes.
So we'll put a equation in there to divide it.
Well, yes. I'm getting to it. Thanks for, it's all good. It's all good. Okay, so now we're getting to a point where we need to put in a list, okay? We kind of skipped over lists last week, as in we actually did a lot of list coding and we ignored explaining it a lot. Lists are important. They're effectively something that you need to understand to go from being like absolutely fresh, never seen grasshopper before to being able to do some like pretty interesting things. Last week, we were able to produce multiple outcomes by using lists, okay? Now, if you want to create a raw list of numbers from scratch, there are two really easy ways, okay? There's series, and these you'll find these both under set. So there's a series and there's range. So what series does is it takes a start number under S, a step number under N, and a count. So if I said start at 10, step up by 5, and do that 3 times, then I'm going to get an outcome of 10, 15, and 20. Okay? Really easy stuff, right? It's a series that steps up. That can go in negative, and it can produce any number of outcomes except for negative outcomes, because you can't have a negative number of items. So we can see here that we have a start default of 0, a step default of 1, and a count default of 10. So we're going to get a series of numbers that go from 0 to 9. There's 10 numbers and they start at 0. Yeah? Range works a little bit differently. So range takes a domain and it splits it up evenly by a number. So in this case, it's going to take a range of 0 to 1, and it's going to split it up into 10 equal segments, giving us 0, 0.1, 0.2, 0.3. Now, I know Christina explained what domains were in class very quickly, okay? And the best way to describe them is a single object. So we can see here, if I quickly go create a range, a domain parameter. A range is a single object, so you can see in this list, there's only one object in it, and that object is something that says 0 to 1. So all a domain does is define on the infinite line, which is numbers, yeah? So if 0 is here, and we've got negative infinity and positive infinity, a domain just defines a location on that line, and another location, and it defines that boundary as a single object, okay? It's really useful to do a whole bunch of things, especially in this case, we can say take 0 to 1 and divide it by 10, and that'll give us these values. But just as a little side note, we can see here the minimum value is 0 and the maximum value is 1. That doesn't mean domains have to have the small number on the left and the large number on the right. You could have a domain that goes from 10 to negative 20. That means the start of the domain is positive 10 and the end is negative 20. So just consider that might become important to you later down the line. And I know it will, because we'll deal with it in later assignments. But for now, is everyone sort of clear with what a domain is? Okay, it's a way of saying any number that goes in between these two numbers. Yeah. So if you were to consider that 0 and 1 is the start and end of a reparameterized line, and I have a component that takes two numbers and divides them into segments, what could I do with this list of numbers in regards to what we're doing with the finger join? Really simple question. It's not a trick question.
Equally for...
It is being divided equally, right? So what we can do is we can use these numbers to divide the curve, right? So we've got the shatter here, which is being divided with one number. But if I were to shatter it with all of these numbers, then we're going to end up with 10 line segments. Okay? Even though you can follow along, like you can obviously connect things the way that I've connected them, but does that make sense? That's the most important thing. Does that make sense? So instead of just dividing by one number, or shatter by one number, we can shatter by multiple, and we therefore get multiple outcomes. And this is like why lists are cool, right? Because we can do stuff 10 times instead of one time. Everyone good? Yes? Your what? She said that to 1. That, yeah. No, 0 to 1. Yeah.
Can I ask why we are using domain? Because domain has almost a similar definition with range. It's from
Of a what?
the similar definition with range.
With
Range.
range.
Yeah.
Sorry, say that again.
It's from A to B. A domain is also means from A to B, and why we use domain?
Because what range does is it divides a domain. So we need this to be divided.
And
So
we can set this
to a different number. Yeah, so guys, I know like right now we're dividing by 10 by default, but if we put a little slider in, so if I type in, 15, oops. And that means that we can divide by any number. Now, I realize that we can't see this right now, and that's because we're just seeing lines like on top of each other, but we'll see this very soon, okay? Yes?
Why just saying no data?
Just get, if you right click that, set domain, we're gonna make a domain soon. Just say 0 to 1.
Like
0 space and then
just one?
TO
Oh, so action 2. Okay.
and then 1. Yep, and then hit the tick. Yeah, it's all good. Yes.
I don't know. So we should connect this one.
Yep. So, did you delete something in here?
No.
So this just needs to be set to 0 to 1. What we'll do is we're going to actually construct our own in a moment. Okay. But there you go. It's working. Okay, guys. Yeah. Can you? It's working.
No.
It is.
It's working?
Yeah, I can see it working. Just you. I said you won't be able to see it yet. Okay. We'll see it very soon, guys. Yes. Right-click domain. No. Domain. Right-click it. Go set domain. 0 to 1. It's weird that doesn't default. So 0 to 1. Is that? Oh, I think I know what's happened. Okay, guys. Just as a note, there's a little trick that I've done. I've gone and grabbed a range, like so, and ranges have a default of 0 to 1 in them. And just to sort of demonstrate that is a domain, I right-clicked that and said extract parameter, which is how it created that. And so if you go and grab a parameter from scratch, domain, my bad, then that's going to be empty. So that's why that's ended up empty, right? So that's how I've skipped over that particular issue. Cool? But we're gonna construct a domain very, very, very soon. Okay. So just to demonstrate, we can see here. If I just go grab the start end points of the curve, because you'll be able to see them. Then see, now that I've plugged them in, we're seeing the start end points of these curves. So if I edge this up and down, then that will show us, okay, there's actually an increasing number. We don't technically need this. This is that's just to demonstrate that they're there. Right. So we've shattered the curves in regards to what we've done with the finger joint, right? We've divided them into segments, And now we need to split them up into odd and even, yeah? Or true and false. Does everyone remember how we did that last week? Yep. So let's go grab a dispatch. What I'm going to do is I'm going to hide everything, and I'm just going to grab a dispatch. And if I grab a curve, we can see the alternation. Like if I also hide dispatch, we can see that sort of dash pattern that it's creating. Okay. Right, and that's because we've got a default pattern in here. So I can also create a pattern, and we're going to say the pattern is 0, 1. And if you remember in class from last week or in the lecture today, if we want this to be understood as a list, we need to right-click the panel and select multiple line. So that'll now plug in. So if just without sort of thinking about this in 3D, and just sort of ignore what I'm doing here. This is just to help demonstrate this a bit. We'll deal with this in 3D very soon. What we've got is we've got two lists of lines that have alternated, right? So instead of having, like last week, alternating points, we've now got alternating lines. And what were we going to do? We were going to offset one of those lists. So offset, if I quickly go grab offset, and the offset that I think that we should be using at the moment is offset curve loose, purely because it avoids some issues. But we can see now if I offset these and I put a slider into offset, we start to see that those alternating curves split away from their friends. Okay. Now this is something that I don't expect you've followed, because if we do this in 3D, we run into a problem, and that is if you were to take a curve in space. And if you were to take a curve in 2D, so for example, all the lines that I draw on the whiteboard are technically 2D. They are held onto the whiteboard. We can't pull them off. They can't go to 3D. They are stuck in their plane, right? So there's only one direction, or two really, that our line could offset. So if I have a line here, then this line can only offset in this direction, to the left or to the right, yeah? Right? Or for example, if I draw a circle, then the circle can only offset inwards or outwards, yeah? If we go back to the line, if we have a line in 3D space, right? And we want to offset it, which direction does it offset? Yeah, so for example, this line here on the whiteboard is bound by what? By its plane. This is a plane, right? But this line is not bound by any plane, yeah? So which way does it offset? It is infinite number of directions that it could offset, yeah? And we want to limit that to a plane, yeah? So if I've got a triangle that this is relating to, a triangle made of plywood, right? And we're offsetting, we should be using that triangle to define the plane that curve can offset. It's maybe better. So if, right? Because we don't want this curve offsetting like this, or going all over the place. It has to be in the plane, or otherwise when we laser cut it with plywood, the laser doesn't understand 3D, right? So you can see here the offset curve. It has a curve input. It has a distance. What's the third input? Right, okay? And that's because you're going to have objects that you need to define those. So, what are the what are some things that define a plane? How can we construct planes? What was it? Two vectors, okay? What if I say two vectors, so if I have a point, right, and I define a vector, yeah, and I have another vector, right, we could almost say that you could also say that as 3 points, yeah? What does 3 points always make if you connect them up? So that means triangles are always planar. They're not always surfaces. If you fill that in, then it is a surface. But you can have a triangle that you go through, you know, like the triangles that musicians play with. You know, you can put the stick through it. It's not a surface, still it's a triangle. Yeah? So we can make planes from triangles, we can make planes from points, and we can make planes from vectors. If a surface is planar, we can also just extract the plane that it uses. And if you were to analyze a surface's plane, where do you think you'll find that component? What are we doing? What type of geometry are we working with? There's two types, right? What two types of geometries am I talking about at the moment? Surfaces and what else? Planes. So planes belong in what tab? The vector tab. And surfaces belong to surface. So if we were to analyze a surface's plane, where do we think we're going to find that particular component? So this is a bit tricky because not all of these are labeled the way we want them to. There's one there that's it's like a little bit cryptic. It has the word plane in it. What is it? You don't look at mine, look at yours. Yep, is planar. So is planar, if we grabbed that, is planar. The cool thing is, if we plug a surface into this, so the surface that we're going to use, we'll say is the first one. So if we plug our first surface into is planar, what does that give us? It gives us two outputs. What's the first output? True, but what else could that be defined as? Yeah, so it's a Boolean that defines whether it is planar or not. So a 1980s car, is it made of, like if I take one of its surfaces, would it probably come out as planar? Yeah, but like a 2020 car or 2018 car, if I grab one of its surfaces and work out if it's planar, would I get a true or false? Right, if we get a false, right? Like this bottle, it's not planar, right? So if I would put this as a surface in, it would come out as false. The output that we want though is the second one, which tells us the actual plane. Cool? And we can see it. There it is there. So what we're going to do is we're going to use this plane to control the curve. Okay? So if I bring that triangle back, we can see now there's the plane that's extracted from it, analyzed from it, and if we slide our offset from that, we can see that the lines are offsetting along that plane. Okay? I can see you look very confused. You're doing the whole like, I don't understand move, okay? So what don't you understand? What's not going right? Yep, so we want planar. Yep, and so the output of that So the output here, this tells us whether or not the the surface is planar. So it is. And then what's this? Ah, okay. And then this is the plane itself. Yeah. So we can see that. We can see that there. There's the plane. There, right? And this is the plane that we want. We don't need this anymore. So we've got an offset here. This plane is now going and defining the offset, and we can now see you can see these lines. Hang on, let's hide these. You can see these lines now, right? They are being offset along that plane, yeah? Relative to the triangle. Cool? Does that make sense to you? Okay. Yes.
I'm a little confused on what this actually does.
Okay. Let me answer that in a moment. Yes?
Sorry.
What's the matter? Okay, guys. Just to repeat, what we're doing is we're taking the first triangle, yeah? Taking the first surface triangle, and we're trying to work out how the finger joints are relating to that particular surface, yeah? So we're plugging our first surface into is planar. Those of you who didn't work that one out, yeah, you've got that now? You've got it? Back corner? Got it? Okay, and to explain what is planar does is it takes a surface and it tests if that surface exists on one plane. If the surface curves, so for example, if I were to plug a sphere into this, then it tests if it's planar and it says, no, it's not. It's not planar, it's false. And therefore, you know, you're going to get a plane, but this plane's going to be like, if any, you don't want that plane, right? Because it's not defining anything. Okay, it gives you the first plane in the surface. So it gives you the plane at topology 0, 0. But we'll talk about that later. Is that clarifying it for everyone?
But why do we need this thing to test whether it's...
Because we've got a line in 3D space. Yep, and we want it. Sure, yeah. Guys, if I'm walking around and you want like the screen to be bigger, then just stand up and move it. Oh. Okay, so this is planar, right? And if I have a line on it, like so, there's a line, then that line, if we want to offset it in 3D, right? If I were to take that line and define it with a pen, yeah, so there's a line in space. When I offset it, which direction can it offset? It can offset this way, or this way, or this way, or this way, right? Dude, I'm gonna need that. Dude, I'm gonna need that. I'm gonna need that. Okay. So it can go in every direction, right? But we've got a triangle. We've got a triangle, right? And we want that line to only offset in one direction. So we need to define a plane for it to be restricted to be able to do that. Yeah? Cool. You got it? Does that making sense to everyone? Okay. We're already making things way more complicated for ourselves. Okay, but whatever. Okay, so we've offset our curve. And that's been offset in 3D space. So I should be able to see that We can see them now offset. Now, I need these two. What's the next step? Where are we up to? We've split them, we've offset them. Now we just need to connect them, right? Now, that's a very important word because there is a component in Grasshopper called connect. And what connect does is, just to demonstrate, if I draw two curves, don't follow along, this is just a demonstration. I think I need to flip this one. If I've got two curves in Rhino, and I'll bring them in as a list, what connect does, connect curves, is it joins them up, okay? But the really important thing here is that it will only connect up curves that are in the same list. Okay, so you can see here, I've got two curves, and that's what the connect is connecting up, right? But if I have a third curve over here, and I have a list like so there's a list of one item, they're in a different list, right? So it's ignoring it, yeah? So you need to be able to put your curves into this component in the same list, okay? Now, we dispatched these lists. So we dispatched the curve into two separate lists, right? So we've turned one list into two. There is a component that allows us to take two lists and make it one again, okay? Merge, incorrect. It's not merge because, okay, let me show you what merge does, right? So if we take these two lists and we merge them together, we're effectively saying, I think you're explaining exactly what I'm about to explain. So if I take these two lists and I merge, then what it does is, there you go, that's why I needed that power supply. What it does is it puts the first list first and the second list second. But we don't want that, right? Because we actually want the first item from the first list and the first item from the second list to be next to each other, not half a list away. That is charging, and that is still recording. Excellent. Excellent. Okay, guys, so if I were to merge these, guys, if I were to merge them and then connect them, then I get this mess, right? So just to go back to this pseudocode, if I've got, let's clean this up a bit. But yes. So I've got two lists, like so. I've got a list with 0, 1, 2, 3, and then 0, 1, 2, 3. What we need to do is we need to say this is 0, then this is 1, 2, 3, 4, 5, 6, 7. So then when we run the connect will then connect them up, right? So we want to do effectively the opposite of dispatch, okay? And the opposite of dispatch is weave. Just, that's what Grasshopper calls it, okay? So let's go grab weave. You'll find it very close to where dispatch is, under set in list. And weave's actually a lot nicer in regards to its labeling. So you know how dispatch sends 1 to which letter? So 0 goes to which letter and 1 goes to which letter? 0 goes to, and 1 goes to, obviously. But if we were to plug 0 into our this pattern into our weave pattern, 0 goes into where? No, so 0 is 0, right, in weave, and 1 is 1. So at least it doesn't confuse 0 to A and 1 to B. At least it's 0 and 1 is 0 and 1. Yeah? Okay, so if 0 goes to B and 1 goes to A, therefore our A output, where does that need to go into the weave? Yep, it needs to go into 1, and our 0 output needs to go into, so our B input goes into 0, obviously, because it's left over. And then if we were to connect them up, and just as a note, in the connect curves, right-click G and select position, and then right-click close, or C, and select false. So that is, you want to put in a Boolean, just to make this a bit easier. We're going to put a Boolean into G, which will be false, and also put that into L. And if I hide everything but our connected output, we have ourselves a zigzag. C is close. So we just want, oh sorry, C is the curves. The curves go into C after you've woven them. Okay, right. I'm going to, so is everyone at the point where, I'm going to get rid of connect curves. Is everyone at the point where they've woven the two curves together? Everyone's put all the curves back together. So now we want connect curves. So we want to connect them. Now connect curves has a few variables, but we just want to have the setting on those set to a certain way. So connect curves takes a list of curves. So if I connect them, see how we get this super funky, weird, wobbly thing? Okay, so the two variables that we want to change to make this nice and finger jointable is if we get a Boolean toggle, which you can find under input. That's probably the thing that I skipped over. Yeah. So Boolean toggle, this is a really nice little thing that if you double click it, it turns to true, and if you double click it again, it turns back to false. Cool, so we want that set to false, and we're going to plug that into both G and L, and that will then, the parameters will set. Now the two parameters that I changed, the G is its continuity, so that is the type of curve that it generates to connect. So you would have noticed that it was generating something that sort of looked like this originally. So that's just it saying, okay, I want to make a tangential curve connection between the two. So this curve has to be tangential with the input and output of these. And then the L, or the loop, is effectively, if I gave it a shape that looked like so, if I gave it two lines, then if the loop effectively just means that it wants to connect itself back up and close itself. So what we're doing is we're just saying, don't loop. So what it was doing is it was actually like looping back to create a closed system. We don't want it closed, we just want an open system. Okay? Cool? Okay, we've got a lot to get through. Huh? No, sorry. You might have to talk to someone. Are you Yeah, are you sure there's no there's nothing. It's all on this wall? None on that wall? Serious? There's no power through here at all.
Only there.
That's stupid. The fact that I haven't put like more than one power board in a university like theater. Yeah. Yes?
G's position.
Yeah, position, that's good. That's perfect. Yep, that's perfect.
How do you make it?
L
Yeah, that's done. It's perfect.
and C.
Perfect.
Okay.
So you should be able to see this. You should see this? See the little finger joint? Yeah? Cool.
That's one outside.
So you're not going to be able to do that. Okay. Well, if people have only got 30%, then I've got to be quick. Yeah. Maybe you guys, this group here, who's on power at the moment? And you need power. Really? Seriously? Is it what? Because you don't have a battery in there. Did you buy one without a battery?
No, I bought the battery. The battery's not working.
Right.
It's 6 years old and I don't know if I
Okay.
can replace it.
Okay. It's probably worth buying a new laptop.
Yeah.
And no, you can't do that. Do not do that.
We can have someone run.
No, it's just there's a door, and the cable's literally like a tripwire across the door. Like you should not do that.
We can run to the red center.
Maybe they can give us a different word.
No. The problem, the other thing is if everyone's running off the one PowerPoint, then the likelihood of it like shorting out is really high. Like, is there a power board there?
No.
So no, the guy that brought a power board last week didn't bring it this week. Okay, I'm just gonna have to deal with it. I'm at 17%. Someone can use my input now. Those of you of charging, if you're at a certain percentage that the battery can, yeah. That does not sound good. Okay, guys. Someone, you work it out. I'm going to keep teaching. Okay, so we've sort of slightly run into a small problem, and that is that you're probably very unaware about. So if I were to finger joint a box, geez, they don't give us that much space, do I? If I were to finger joint a box, and like the box in plan looks like so, right? It's got thickness, yeah? And I were to look at this edge and look at this edge as an elevation. So this is sort of like us looking at the box from the side, okay? There's the ground. Then if this was finger jointed, then we always want to create our box finger jointing so that it sits on the edge in a way where the elements clash technically. So if you were to look in plan, the finger joining teeth, they sit in the same area in plan, yeah? Which normally means that when we do finger jointing on something like a box, we just pick the edges and go in, yeah? We just offset in. But in this case, we need because we're dealing with a really complex geometry, and unfortunately, we don't want to go out or in. We actually want our finger joints to be defined on a center. So that means, actually it'd be better to draw this in a different color. That means if this was the line that we've generated, we actually want the finger joint to offset off the center of that, okay? And that's purely in regards to the complications of how these things get made because you guys have to build this thing, right? So, and you've got an hour to finish this tutorial. Okay. So we need to center this. The easiest way to do that is we need to grab our offset curve. We need to copy it, and we need to also offset the the curves that come out of A. Now, if we're offsetting the curves that come out of A, which direction do we want them to go? The opposite direction, right? So that would mean if we're offsetting by a positive number in one direction, what would be the opposite direction? Negative number, right? So all we need to do is right-click D, which is the offset value, select expression. This is a really quick and easy way of changing numbers as they go into things. And in that expression, we're going to write negative x, which will be the variable. That's going to give us a negative. But then our slider, if I'm going to be making this out of 3 mil ply, what do I want that slider to be? Right. But if I want this to define 3 mil, what value would this be? The one of the offsets? 1.5. And so what is that if you take 3? What do you have to do to 3 to make it 1.5? Halve it. So we'll go divided by 2 or /2. And we need to do the same with the original offset. So we need to right click the D, go to expression, and this, in this case, we want x divided by 2. And so now as I slide this up and down, you'll see that it offsets off the center line instead of offsetting in one direction, okay? Geez, there's no way we're going to get through this in one class. Negative x divided by 2 and x divided by 2. Okay, we're not even halfway. Okay. Okay. So we've now made a component. We've now made a process that takes a line and works out how to it generates a finger joint on it, right? This is where things get a bit muddy because to produce this on the next line. So, for example, our triangle right now, like if we were to get the edges of that triangle, right now we've finger jointed one edge, and we need to finger joint the other, and then we need to finger joint the third as well, right? But that means the process that we've just done to the first line, what do we have to do to the second line? The same process, right? Now, I honestly would, if I had time, and time meaning if I had a week with you guys, I would teach you guys how to do this in a really clever data centric way, right? Where you can apply this to any job anywhere and it will do this. But in this case, you guys are going to have to take some of these steps manually. So we need to basically turn this into a process that is copyable and is applied to the next edge, okay? So we need to copy this process and paste it on the next line, okay? And a way that Grasshopper helps with that is a function called cluster, okay? Clusters are dangerous things. I say they are. They can actually cause rather clusterfuck. So just be really careful with them. They are really good for creating. They're really good for creating something that a process that needs to be repeated, and they actually if you copy and paste them, if you change something in one, it's going to change the other clusters. Okay, so just to demonstrate, I'm going to create a panel. I'm going to write Andrew is awesome. And I'm going to turn that into a cluster. So I can do that by selecting the panel or selecting the elements that I want to clusterize. Clusterize, I guess. Hit spacebar or middle click, and then we've got there's a little package button up here called cluster. So you can see that then turns that into like a custom Grasshopper component, my own Grasshopper component, right? and we can see the output is Andrew is awesome. Yeah? If I copy this and plug this into another panel, it's going to be hard to see that. So then I get, is it going to let me? I'm going to get Andrew is awesome, right? Okay. So these two things are basically the same. If I double click into this, it then brings in, we're in the cluster environment, and I can now make a change. So for example, I can say Andrew is annoying. And if I save that, we can see that that's now affected both. Yeah? It's not just affected one. They're instances of each other. They are entangled, okay? And if you want to make a cluster that isn't, like you want to copy it and you want to make it so that it's not entangled, you can right-click it and disentangle. There? So now if I go, Andrew is tired, then we can see that those are no longer copying each other, okay? So just be mindful of that. So what we're going to do is we're going to take this process that we've made, we're going to just set it up in a way where it just needs to be a bit clean in what its inputs and outputs are being defined as. So we're going to set a geometry output here. We're going to put in a surface geometry here, which is going to be our first surface. So our first surface will then plug into the brep, and is planar. And if we're gonna, just to help the labeling process, we'll right-click surface and name it like first, third, first surf. Then we need to grab another surface parameter, plug that in. By the way, if you right-click any parameter, you'll see a little button in the top right-hand corner. If you click that, that'll toggle through a few of the display settings. So in this case, we've now named our surface parameter first surf, and if we click that button, it'll show the name of that. So if we right-click the second surface and call that second surf, and also hit the button. There we go. That plugs into the second one. We'll leave the domain as the same. So we've got, what we're seeing here is a clear definition of two inputs and one output. And we can even name that output finger joint. Now the really important thing is this final output, we need that to be plugged into one more parameter, because what we're going to do is select this group of components and we're going to cluster them. And so we need to, if by selecting this last one, if it's not connected to anything, it's not going to be read as a cluster, an output in the cluster. So once everyone is at this point, and I'm just going to leave this up. Actually, what I might do is I'll copy it. So once everyone's at this point, like so, then you hit spacebar, hit cluster, and that will then create a single component. So once everyone is at this point, I'm just going to leave it up. There'll be, you want to cluster, turn it into a cluster, okay? This point. We're taking shortcuts here, guys. Like this, I copied this and then made a cluster. So that's what the cluster will look like once you do this. No, you don't have to. No, don't copy it. Cluster it. Yeah, connect. Yeah, so connect. You just need to make sure that this. Once you go out of connect curves into finger joint just needs to be in there. If you don't do that, it's going to cause this problem. You're not going to get an output. Okay?
So just highlight the whole thing in the cluster?
Yes. You want to highlight the thing that you want to turn into a cluster. This is where there's a dangerous. Clusters are dangerous because if you don't make your cluster robust, really robust, capable of handling any like inputs and changes to it, then there's a likelihood of it breaking really easily. Okay, but in this case, I'm pretty confident that this will turn into a cluster. Huh? You're nervous? You should be, right? We want to be careful when we cluster things. Huh? Runtime error?
Yeah.
What do you mean?
Like it failed from surface to surface.
Oh, that's because you grabbed a surface parameter.
Oh, okay. Well, I just missed that one.
Did you just say lol? Okay. I'm getting old. Yes? Perfect.
Oh, okay.
How to do this? Just. Where?
You've already done it. There, you did it. You've clustered these things. Did you just make them? These two? Yeah. No. Be careful. Just let go. Okay. So, what you need to do, guys, is you need to select the whole system, right? You need to select all of this. Yeah?
Yeah.
But you also need an output here. If you don't have outputs on the end, it's not going to read them.
So we should have two.
Yeah, you need two. You need two because what we want to do is we're going to select. This is going to go into the system, and this needs to stay outside the system. So we can select all of these, and then we can say cluster, and that's now created a cluster. Okay. So if you double click that, you can go into it. Is everyone clear with this? Yes? I knew this would be problematic. Yes?
I realized disconnect is right.
Yeah, but this just needs to go into one. Yep. And what expression do you have there? So that needs to be negative x divided by 2. Cool. See it's working now?
Yeah.
Now is he gonna help you cluster it?
Yeah.
Yeah, good. How are you guys going? Yeah? Okay, so you select the system. Now we're not selecting this one. We want this surface to go into there, and we want a second surface to go into here. Right. So what we're going to do is we're going to select this to cluster, but to make sure that there's an output, we just need to copy this twice, have it plug in twice. We're not going to cluster this one, we're going to cluster this one. So if we select all of this as a system, spacebar and cluster, we've now made...
It will be together?
Yeah, it's all together, and so if you double click that, we can go in.
Oh, thank you.
No problem.
So you can still edit the cluster?
Yeah, you can double click it to go in.
So cluster is for this one.
Perfect. Just be careful, this might work. Hit spacebar, I've never seen this one do this before. Oh, hang on, wait, before you do that, cancel. C first?
Yeah.
That should also go into A.
Going to
A.
so
A, yep.
is this one.
Yeah, but then that also needs to go into S now.
So
Like this.
oh, I know what happened.
Like that.
Okay.
Yeah? So now you can select all of this. Yeah, mate.
That's why it's right. Still
No. Don't select that one.
Oh.
You don't have a mouse?
Yeah. I didn't take it.
Okay, this just needs to be more than one, right? Because we want to divide our curve more than once. We need it to be divided by 10.
But 0 to 10?
It could be 20, it could be 100, right? So if we set that to 20 and go okay, and now if you pull this up, see now there's elements going in there. Cool?
Yeah.
But you're going to get this guy to help you make a cluster, right? Or is this guy got a cluster? You got clusters? Cluster?
Yeah, but my thing is on diagonals.
So all that's doing, so you've you're using B in both.
Okay.
So A goes to 1, yeah?
Yeah.
So therefore, we want A going to 1.
Okay.
Cool? Did you get that?
Yeah, I get it.
Sweet. Right, okay, we just got to keep going, guys. This is almost done. Cool. Pardon?
The other finger joint bit.
Yeah, so you just need to make sure you need to select it so that it's got an output, like outside.
Okay.
If you select that one as well, then it's not going to give you an output. Yeah, so we need that. That works. Guys, huh? That's it. That was it. That's all you had to fix. Guys. We've got 45 minutes and we're nowhere near finished, so I've got to keep going. So we cluster this, and we've now got a system where if I copy this cluster, right, that means I can apply it to a new edge. So if I go back to our original system, the first surface is the surface that our finger joint is relating to, right? So that's the surface that we're getting the plane for. So we always want, in this case, if we're generating all of the finger joining edges for this, we always want the first surface to be the one that it's being generated for. So then the second surface is, in this case, it's going to be intersecting here with this guy. So if I now plug that in to the system, I get a finger joint between those two, right? And if everyone remembers, this is actually belonging to a radial system, like so. So our third surface is actually going to be, our third finger joint has to relate to the surface that is this one, but shifted one in that list, right? You remember? So what we need to do is also shift our list before we pick an item. So we'll go shift list. And in this case, it looks like it needs to be shifted positively. No, it needs to be shifted negatively. Okay, so that now, if I show this back again, we've got our original 4, and now we've got a shifted list for this guy, but it's now giving us the item to the left of it, right? It's like the next set, and we'll need to do this the opposite way for when we do the finger joining for this triangle. So if we copy this again, and I'll just preview the output as we do this. So we copy our clusters again. We can now use this third input as the input into the system, and we get the finger joints there. Okay? So all we've done is we've made one system, a rule system. We've turned it into a cluster, and we've copied it 2 more times, and we're just putting in a new set of inputs. So this one is the one adjacent to it further out, and then this one is the one adjacent to it, but clockwise. And then that then gives us 3 finger joints. But we've now got a problem. Is everyone at this point?
With the shift list.
Yeah, list.
What's the left end connected to? Is that connected to the third surface? Or the
It should be it should be connected to the second list of surfaces.
okay.
Surfaces 2. And the shift value that I've put in there is -1.
Wait, how do you put that value?
You can either right click it and set integer and type in -1, or we can grab an integer component, which you can find here and do the same, or you can grab a number slider, right?
Can we put the geometry into the cluster?
Yes.
The geometry. Okay.
As in, you can plug these new geometries into, if you copy the cluster and you plug in, so for the first cluster you had these 2, and for the second cluster we just plug in this guy here, right?
So can we put the geometry into the cluster?
I don't understand how that's different to what I just said. What do you mean?
The geometry.
Which geometry?
That's single.
The function.
Yeah, function.
This one?
Can we put it in cluster?
Like this? Oh, no, don't leave that out of the cluster. You need that so you can preview, right? It's just a nice little organization. Like Grasshopper's now made these things called relays, which are also useful. Relays are kind of like these parameters, but if you just double click a cable, it'll make a relay. But the problem is you can't drag. Like I don't know what the shortcut is to drag and then just create a relay. So if you want to organize this a little bit, you grab a geometry component, which is here, and then you can plug it in and organize it up. Okay? Does this make sense? Right? Is everyone kind of at this point?
I'm still confused with the shift. Yes.
Right, so the reason we're shifting the list is because if we ignore the shifted one, if we look at this system, right, we've got 4 triangles. But we actually need to also include the neighbors in the system to be able to generate the finger joints that join with the rest of the, So what we're doing is we're grabbing this list and we're shifting it by -1 so that when we pick out the first of that list, it's now instead of it being this panel, Arlene, instead of it being this green panel, we've shifted it. It's now the one negative in that list is now the first one in that list, and we're using that to generate the finger joint.
Gotcha.
Okay, so in theory, we should be able to copy these 3 and apply them. So if I were to just move this up a bit, these 3, now if they were to apply to this triangle, right? Geez, we've got almost 0 time here. If they were applied to this triangle now, like if I disconnect, guys, if I disconnect these, so I'll just start this from scratch. If I have 3, if we're working on this panel, which input does this panel go into? Does this surface? This is the one we want to generate finger joints for.
First surface.
Right, the first surface. So this plugs into the first surface. Yeah? Now, let's say for this one, we want to find the intersection between the green one currently selected and the green one now selected. So where does this one go?
The second surface.
Right. So look, that's now generating a finger joint. But we've got a problem. Can anyone see what the problem is? The one, yeah.
It's like over like extruded.
Okay, look at this one, right? This one is sticking out, right? Which is fine, and then it's going in. But then if we look at this one's sticking out, so they're going to clash. Like if we make that out of a material, they're not going to. You can't make them ghost between each other, right? So the pattern that we used in this dispatch, this 0 and 1, it has to be different for this list, these curves. It has to be different. It has to be almost inverted, okay? So what we're going to do is we're going to go into our cluster. This is too much stuff for one lesson. We're going to go into the cluster. We're going to grab an input, cluster input, which you can find under parameters and utilities. And we are going to plug that into our, no, we don't want to plug it into a parameter. We're going to plug that into a Boolean parameter, okay? And that Boolean parameter is now going to be replacing 0 and 1, okay? And all I did there was I held Control-Shift to drag that. And you'll see the whole system break. But that's fine, because we're going to copy 0 and 1. We're going to cut it out. So we've now got a Boolean going into here. So if I save this now, we can see our clusters have now got a new input. You can see, what's the new input? Right, so the Boolean, if I plug my 0s and 1 panel into that, the system begins to work again, right? Because it's reading that those values in, yeah? So I need to use 0 and 1, but in this case, I need to invert it to 1 and 0. So now, because we've inverted that pattern, we can see how the finger joint now it's actually not clashing. Yeah? There's 35 minutes. It's not enough time. Okay, everyone cool with that?
No.
Okay. Look. If I finger joint this, right? Like so, the pattern is 0, 1, 0, 1, 0, right? Yeah?
Can we have the full screen while you do that?
What do you mean?
Yeah, just a script. Yeah, great, thank you.
Okay, so we've got 0, 1, 0, 1, 0, 1, right? Guys, if I say 0 is going to offset this direction and 1 is going to offset this direction, if I draw the same line, but I want the outcome to be like so, then it works the same, right? 0 is this direction, so that's 0. But then the ones that go in the opposite direction are 1. So we just need to change our pattern from, instead of being 0, 1, 0, 1, 0, 1, we just need to change the pattern to 1, 0, 1, 0, 1, 0. Does that make sense?
How did you invert it then?
How did I invert it? What do you see typed into the list here, into the parameter? I've just typed 0 and 1, and then you can see here I've typed 1, 0. There is too much to do.
Why do you have the 5?
Yeah, so what I've done is I've plugged this into each of the Booleans, and I've plugged this into each of the Booleans. There's too much. We've got you've got 5 because we need to find the neighbor, Blair. So Blair, there's 4. If we've got 4 surfaces, but we want to find the finger jointing on this edge, we need to get the neighbor. Yes? So we need to shift the list by -1 to pick out that to make that third intersection. Does that make sense? Okay. We've got 30 minutes. Yes. So Blair, we have to do this again, okay? Because, look, we're working now with this surface, yeah? We've made the finger jointing for that in that direction. Can you see that? Then we need to find the finger jointing for not this surface, but this surface, yeah? Because if we're working on this green one, this on the right, we now need to do the finger joint that goes to the one to the out, right? So that then plugs into our second finger joint edge, which then generates this nice little finger joint, yeah? But then our third one, where's the surface for that? Where's the third finger joint going for the second panel? But where is it? Where is it? Just to help explain to Blair. Blair, are you paying attention?
Hidden adjacent
No, I
to.
didn't pick up.
Blair,
Where are you?
look. We've got three edges that we're creating figure joints for, right? Where's the third edge in the system? Look. If I show it, where's the third edge? It's this one, right? So that is just this list shifted by 1. So I'll just pull it off to the side down here. Shifted by 1. This is crazy. Yeah? And then we pick the first of that list. So that's this one. So this then goes into the second surface, which then, if I just show these surfaces, that then gives us the third finger joint edge. Does this?
How do I find the 7? What's 7?
That's an index. It's an integer. If you right-click it, you can set that to 1, or it'd probably be easier for me to put in a number slider in for you guys. So number slider from 0 to 1, if we set that to an integer, then, okay, there you go. So that just needs to be 1, and now it's shifting it correctly, and the same applies up here. I know, guys, I know this is a bit intense, but I need to get you to one more thing. So let's assume, like if we can do this for the first 2, then we can obviously do it for the last 2, right? But I'm not going to do that this lesson. There's too much time. Yeah? Not enough time. Not enough time. We've got a problem. I've got a problem. And our problem is, look at this mess. Isn't it super messy? It's really messy, and it's not going to work. So what we need to do is we need to jump back into our cluster, and we need to make a change. And the change is the domain, okay? The domain currently is taking a number, it's taking a line and it's dividing the line by its full length, right? But if I were to change that domain with a construct domain, I think I actually have to put bifocals in here for it to work now. There we go. So if I were to put a construct domain in, so construct domain, we can find that under math in domain. So what that does is it lets us define one with sliders, right? So guys, you really should be paying attention to this because this is gonna, Blair, pay attention, please. So if I have a construct domain, that you can see I've got two number sliders going into that, and as I slide one of them up and down, it's changing the start and the end of that domain, right? So if I want to edge our like division zone, which we're using in this range, so that it's sort of like moving away from those edges so they're not getting messy, then all we need to do is have one variable that is helping define both the start and end of this construct domain. The start we'll leave alone, but in the end, what we're going to do is put the expression 1 minus x. So what that means is if I set this to 0.1, it's taking the start at 0.1, and then it's giving you what? 1 minus 0.1. So that'll give you 0.9. So if you then use this instead of this domain in the cluster, so just so that everyone's aware of where we are, we're in the cluster, we go to roughly the beginning, there's a domain, we've got a range, and what we're going to do is we're going to replace our range with the domain, our constructed domain. As I slide this up and down, guys, you see how it's stretching the split, and there's going to be a certain point that it breaks. Okay, so what that's doing is it's allowing the system to avoid the mess on the ends. So that's good.
But then how do we do it?
That plugs into range, pardon?
Oh, it's okay. That was irrelevant.
So like the edges doesn't matter if they stick together or not, right? Like the end point.
What do you mean?
Like the end of the two the two lines.
Yeah.
And then they have no kind of
Finger joint. Well, no, what you'll see, because now this is applying to all of them, right?
Yeah.
We can see now that, shit. Let's go back. But guys, by the way, the reason it might actually be easier if everyone just sets this number to be even. So the number that goes into range, if you double click it and just set it to be even, that's actually going to fix a few of the problems. So we'll set that to even. We'll then go back to save and close. And then remember how I inverted this and set this to 1 and 0? We actually want that back to 0 and 1. My bad. So you can see now, even though that we're avoiding that sort of messy edge, that this edge is stepped in and this edge is stepped out. Does that make sense? So the system still works. It's just moving the finger joints away from the edges so that they don't clash with each other. Okay? But there's one more thing that we have to do, and that is if we want to finish this triangle off, we actually need these to touch each other. Okay? Because we need to work out where they're intersecting so we can then split them and then get the bit that's left over in the middle. Okay? So if we go back into our cluster, 25 minutes. Go back into our cluster, go to the very end of the cluster, and here we want to apply a utility to our curve called extend curve. And in extend curve, we just want to extend that by, let's say, 20 mil. Okay? So I'm going to grab a slider. And we're going to plug into, so what this does is it extends a curve by a distance on both the start and end, so start being L0 and end being L1. So if we plug a number into both of these, then we will effectively make our line longer, right? So as I slide that up and down, it makes it longer. Cool? Oh, we're still miles away from being finished. And then that needs to now plug into your finger joint output, because that then gets output from your cluster. Okay. So let's just forget about this. Everyone kind of understands this, right? The fact, everyone understands the fact that we can use clusters to do a process to more than one thing. And because we've created a system like this, if they clash, we can play with the figures to make them not clash, right? Yeah? Okay, so if we just focus on on this guy, let's just focus on this particular system, right? We need to get this so that it's laser cuttable. Okay? And we could technically, this actually works. You could put this in a laser cutter and it will work, because the laser cutter is going to run down this line and cut, and it's going to run down this line, and a piece will fall out of the material, but we're just cutting way too much, right? We just want to cut what we have to cut. Now we've got 25 minutes. I think we can make it. Huh? We can make it. Okay, so in my system, if I start offsetting and extending and trimming, what happens is when, you know how we've sort of got this diamond kite diamond, whatever, shape, when we start offsetting and creating these finger joints, there's going to be clashes in the neighbors, okay? So this one is going to clash with this one at the corner, and we want to avoid that, okay? And there's a potential that this will clash, and this is going to end up being a bit messy because there's going to be a bit sticking off the end. This is just something that I know will happen, okay? Experience, right? I've got enough experience to know that we're going to run into these issues. I would anticipate that if you were to just start this from scratch and work it through, you would eventually discover it and you're going to have to go back and fix the problem up. We're going to fix it up now, okay? So what we have to do is we are going to trim every shape so that they avoid these clashes, okay? Okay? But we only have to, so in that case, what we need to do is generate geometry very much like what I'm drawing here, so a circle. But if I were to, like, we know this is a 3D object, so this circle effectively has to be a cylinder. So we're going to generate a whole bunch of cylinders that will then trim our curves back to avoid these clashes, okay? But first, we need to join these so that they are we need to join these triangles so that they're one object, yeah? So to do that, this is too much. To do that, we need to find where they intersect, because we need to know where these two lines intersect to be able to split it at that point, right? So what we're going to do is we're going to find intersect, we're going to get curve versus curve intersection. So if this is our curve, which two curves do we need to find where that intersects? These two curves, right? So if I plug this curve in and I plug our second one in, we get that point, but we don't just want that point, we also want our second point, yeah? So we remember how I was telling you guys last week, if you hold shift, you can put two elements into one input? So I'm holding shift now, and we're forcing this element to find the intersection with two curves now instead of one, yeah? The output of this gives us parameters along the curve. So we're getting 0 and 96. If I reparameterize this curve, then that's going to be a number between 0 and 1. And I'll just leave reparameterize off. But so these are effectively those parameters. And probably like the easiest way to do this whilst maintaining a bounds to what we taught earlier in the lecture, there is a curve, instead of using shatter, so I could shatter this curve at 0.05 and 96.87, right? And what's that going to leave me with? How many curves will that leave me with? Huh? It doesn't matter. If let's say I shatter at 25% and 75%, how many curves will I have as the output? No. 3 curves. If you split an object at 2 points, how many objects do you get? Yep, you get 3 objects. Right. There's another way of getting subcurves out of curves. out of a full curve. And the way that we're going to do that is with this component called subcurve. What subcurve does is it takes a curve and it takes a domain for that curve. What do you reckon our domain is that we want for our curve? Look at the numbers that you're seeing here. What domain do you think we want? 0.05 to what? Brilliant. We want it between these two numbers, right? And a cheap and easy way to make a domain from a list of numbers is with bounds, which you can find under math domain. So if we plug our parameters into bounds, that'll just generate a nice little quick domain from that, right? Super easy, super quick. We've now made a domain. If I plug that in now to our domain, we end up with, if I hide our original curve, we end up with the curve that goes to the extent that we need it to go to, okay? So I now can use this system, copying it 3 times. So we're going to plug our second curve into A, we're going to plug the 2 curves that it corresponds to into B, and our third curve into A, and the 2 curves that correspond with it into B. And we need to also plug these into our subcurves. I really apologize about this, guys. This is more so time issues than anything. Now, why is this causing issues? So guys, and then just to avoid issues, I want you to go through each of these geometry components, and I just want you to flatten them. They just need to be flattened. What? Oh, sorry, my bad. You will need to go through, see this, the bounds, each of these bounds needs to go through and flatten, flatten, and flatten. Right click the N of bounds and you should be able to click flatten. And that should leave you with 3 trimmed curves. Yeah? I know. Is your computer dead, or it looks like you've given up?
I gave up a while ago.
Okay.
I've got to rewatch the tutorial.
Yeah,
I'm
Just like pause and
I'm gonna have to probably, I've skipped over a whole bunch of shit, in terms of explaining stuff.
can you still upload it?
I will.
Yeah.
Straight away. Yeah, I can upload it during the next lecture that I'm in. Okay, so we've got 3 curves here. Now, for this to work really well and to avoid a lot of mess, we need to join these curves so that they become one object. Because they're all touching at their ends, if we use join curves, what that does is it takes a list. So in this case, if we plug all of these in at the same input, it will produce, oh, you bastard. As long as that list is flat, so we need to make sure that the join curves is flat. So I will explain what flattening does soon. We just have to avoid it because we've only got 15 minutes. So we want to right click that and flatten it just to make sure that it works. That leaves us with a single polyline curve. So that is now a closed curve. I can effectively turn this into a surface if need be, like so. And it's something that we can laser cut if it's flat. Yet again, something that we don't have time to explain, something that I'm gonna have to add. I'm gonna have to make a video tonight to help with this, okay? It's just the reality that we're in. Otherwise, yeah, you're gonna have to use Rhino to orient. Either way, okay. So we've got a series of points here that Christina's given us. These are the points from our previous script that we need to basically be generating cylinders on to trim the ends so that they don't clash, okay? Does that make sense? So look at this. See, you know this diamond thing? So we need to generate a cylinder in the middle, we need to generate a cylinder at the end, and we need to generate a cylinder where these two meet. because there's some geometry in here that will clash with it at that point. So if we just trim a little bit out of there, it avoids that issue, okay? So the way to do that is if we just take all these points, we're gonna get there, we take all these points, we flatten them, as in, sorry, we project them, so therefore we make them flat on the ground, okay? And we use those points to generate a cylinder. So we can get a cylinder under surface primitives. So that takes a center point, it takes a radius. Just make sure your project has a flatten in it, because some of these are actually in branches, which is rather frustrating. We're going to set a value in there for the radius. So we can change the radius of the cylinder, and we also want a height for our cylinder. In this case, the height needs to be big. It has to be so big that it just includes the whole model, okay? So we just want that to be really tall, right? You've got 10 minutes.
We're gonna quiz that one, so
Yeah.
can finish a bit earlier.
Just say no.
I'll finish at 1. What a dickhead. Okay. Oh, if you could just finish earlier, that would be really handy. Oh, yeah, fuck you. Okay. So we've made our cylinders, we've made it really tall, we can change the radius. We need to cap holes because these need to be solids for this system to work. Once we've done that, we've generated all the cylinders that we need, okay? These are the cylinders. Any curve that goes in these cylinders, we want to trim it, okay? So we're going to grab this list of cylinders, this capped list. Let's grab a geometry component parameter just so that it's nice and organized. So I'm going to move this up here. So this is the list that we want to deal with. And what we're doing is we're finding where this joined curve is, we want to trim it with this. So you can see here, this cylinder here is going to trim the end off this guy, and this cylinder here is going to trim the end off so that they don't clash, yeah? Okay, quick and easy way of dealing with this is we want a trim with B-reps. You can find that under intersection region. The B-reps, which are the cylinders, go into B, and the curves that we want go into C. The output of this is we get a curve output from our join that is inside the cylinder. Scrap that, we don't want that. We want the curves that are outside, okay? So that is now leaving us with 2 curves, and this is where we're going to use an old component that we used before. So if we want to close this up really easily, we'll just go and grab connect curves. So connect curves, yet again, remember how it created these like little blobby ends? So we want that G value to be true, to be false, to make it a position, giving us a nice straight edge, right? But then, do you remember how we didn't have it looping prior? How we had the false going into L? If I have a false going to L now, what it's going to do is it's not going to close it up, and we need it to be closed. So we want that set to true. And we're almost there, okay? This needs to be done to every panel, okay? Those 4 panels, this has to happen to the 3 others, okay? We've got 10 minutes. This is 3D, yeah? How do we get this into a laser cutter? The laser cutter needs this thing to be flat, yeah? I really wish I had time to explain this. I really do, because it's really important. But this 3D shape now needs to be laid on an XY plane, right? So that the laser cutter can follow it. In the past, I've talked to you about moving. So we can take a chair and we can move it, right? Now there's a process involved where we can take a chair and rotate it, but there's a beautiful system where we can take something and both move it and rotate it, okay? And that process is called orienting, okay? Now if I were to take something that an orient, and I were to say, take this object, the thing that I need to give it to orient is a plane, right? So if I say there's the plane, there's the X and there's the Y, and then I draw an X and a Y, oh, that's not good. If I draw an X and a Y over here, see how this circle, maybe it's better to draw a triangle. See this circle with a triangle in it? That then orients like so, right? So it's just relative to the plane that it's being oriented. So we have a closed curve with this one, and we know that it's planar because we generated it in a planar scenario. I really don't want to go back to the cluster at the moment and grab the plane from that cluster and bring it back and use that plane for this curve. Instead, what we're going to do is we're just going to grab a similar analysis tool which effectively determines whether or not a curve is planar. That then will tell us, oops, no, we want that plugged into this. That will then tell us the plane of that curve, okay? Similarly to how we got the plane of the surface. I'm seeing really grumpy eyes. I'm sorry. So we've got the plane of the surface. We then have the world XY plane. That's the plane that the laser cutter operates in. We just need to orient our outline, so this curve, from this plane to this plane, and you can see that's now oriented it onto the XY, which can then be laser cut. Okay? The steps that I've just taken, as in finding the intersections, getting the sub curve, and then joining them, trimming them, and then reorienting them, needs to happen for your 4 other planes, right? And then they need to be laser cut. In this case, there are 6 rotations, so you need to duplicate those 4 triangles 6 times, ending up with 24, therefore allowing you to make a finger jointed model.
Yeah. Do you want it glued together with one next week?
Yes.
Which glue do you want?
Use Yoo-hoo glue. Okay, now
Are we making this with our own model?
you should make this.
With our own model, right?
No, just make
Let's
this.
just make this one.
I'm gonna try really hard to maybe step through this again. Like I'm gonna record this again. This needs to be recorded again. Like it's more so the fact that we've just run out of time.
When can you understand because do we have to do this laser cutting on the Friday?
No, you can do it Monday or Tuesday. But the point of the fact is that now, okay, there's one more thing that guys. There's one more thing I need to point out to you. Please listen to this. This is really important. And this is important. Some people want to hear me. When I do a finger joint at a 90-degree angle, right, and I'm using a 3mm ply, then what is the distance of the finger joint? 3mm. But if I'm doing a joint at a weird fucking angle, right, what is the distance of the finger joint? We know we can do it with trigonometry, right? I want you to be very careful about what that dimension is. And there's going to be a step that I do in the errata of this. Errata as in things that I didn't do, like extra things that need to be done, which will help you determine whether or not your material will clash with itself. And that will then determine the variable that you need to set. So this might have to be set to 3.5. I honestly would prefer that trigonometry was used to work that out, but I don't expect you guys to do that. I expect that we're just going to slide the number slider to the point where it does work, and we'll just laser cut that, okay? Because like the trigonometry and the geometry functions required to do this is messy. You can see why I would much rather just make a square box, because we can just say that's 3 mil, therefore that's 3 mil, that's 3 mil, done. Yeah? But we're not doing that. We're doing weird funky shit. So the model that you made, the really sharp, high thing, that needs to have a much larger finger joint so that they don't, like, they actually fit together. Does that make sense?
No, but I will think about it and hopefully it'll make
Okay, look at it this way. If I draw it, if I draw a really sharp angle, then this needs to be finger jointed from that point to that point, and this needs to be finger jointed from that point to that point, right? So that distance is much wider than the material. Do you get it what I mean now? So if I finger jointed it there, there's material that's clashing with that through there. That's what I mean. Okay, let's get out, seeing as the next class has a quiz to do.